Our third exam is on Tuesday. This is, in my opinion, the hardest material of the semester. So if this scares you, don't get too scared. It'll get a little easier than this. This is the hardest chapter is what it is. In my opinion, if you can do reasonably on this chapter, you can do well in calculus. The rest of the material, there is some important material for trigonometry to be sure. We're going to solve non-right triangles, for instance, a very important topic, but you don't use that stuff in calculus and your other science courses much at all. Pretty much everything you need to do for your science and math classes, if you can do well in this chapter, you can do well coming out of here. So make sure you do well on this exam. Come by and see me as you have questions. It's only chapter 7. It's 7.1 through 7.5. The problems will all be similar to the homework. I took a smattering of those, which are basically old test problems. Put them on the practice problems on D2L. If you haven't downloaded those and tried them, look at them. If you have questions on that, you've been looking at them, ask them today. I'd be happy to go through them. We're going to spend the whole period reviewing today. Start early on these. These are really long. Don't let it scare you. The practice exam is much longer than the actual exam. You'll see I won't even finish all the problems in class here today. I'll have a lot of them left. You know, just make sure some of them maybe look at it and say, I can do that. But make sure you can do all of them similar to that, because almost all the problems on the test will be similar to the practice test. If you can do all those in a mixed up order, you can do my test, right? I'll give you something that's on the homework that's not on the practice problems, but not much, right? So office hours will be online and in person. If you want to see me, I have office hour right after class today, for instance, just down at the end of the hall in MCS 113. They're not at my office again. They're in the listed classroom, MCS 113 at the end of the hall on the right after class. Or on Monday afternoon, you want to come back then, I have an office hour just next door in MCS 103. Or you can sometimes schedule online office hours at other times. Just send me an email. If you have trouble with those, or you just want another way of looking at it, the free tutors at the end of the hall on the right, it's the computer terminal room. The tags on it says tutor. You can just sit there and do your homework, and they tutor everybody through calculus. They can do trigonometry, right? There are lots of hours, except they're off Friday afternoon, I think. Bring a calculator to the test. You need it on this test probably more than the others. There's things to plug in and evaluate on the calculator. Any questions on the test itself? All right. In person, unless you arrange otherwise. I understand if you have a reason. If you're not feeling well, don't come. I'll let you make it up late. I'm being really easy on that this semester. Kind of a difficult having so many makeup exams, but it does work. All right, so here's what we want to do then is look at these problems here. Is there any particular ones you want to look at first? You've been looking at these. Otherwise, I'll probably go through these mostly in order, picking some of them that I think are the more tricky ones. Okay, well, let me see. Let's just look at the first one here. One thing I might ask you to do, going back to the beginning of chapter, is simplify trig expressions, all right? We're going to want to simplify 1 minus tangent squared over secant squared. All right. What can I do with that? We have these rules of thumb that I'm telling you, for me, work on all the problems in the book. You don't have to follow these rules of thumb. Use whatever rules you want and just do them in your own way. But what I like to do is look for algebra expressions first, if I can reduce this. And then I'll try and apply a trig identity after I'm done with my algebra. And then I'll try, if I'm stuck, or generally if there's more than 2 trig functions in here, I'll rewrite in terms of sine and cosine only. And then the fourth rule that I'll put up at the top, rule 0, if there's more than one angle in here, always reduce it to one angle. So get a single angle. There's very few problems where that comes up, but get a single angle. If one of them's 2 theta, one of them's theta, you can't do anything till you get with 1 angle theta or 1 angle 2 theta. Right? So those are my rules of thumb for doing this. And then on these, let's see what we can do. How about this? What's the first rule? Well, if it's a single angle, they're both theta, that's good. Algebra. What can I do with algebra to that? If I was doing an algebra problem, what would I do to try and simplify that? I don't know whether I put over a common denominator, right? If you have things to cancel, or if you have compound quotients, or you're missing a common denominator, do those things. Most of the algebra rules I'm talking about here are the division rules, canceling factors and divisions, putting over a common denominator, or canceling compound quotients to simplify. So I'll rewrite this as secant squared over secant squared minus tangent squared over secant squared. And now they have a common denominator, I can subtract the numerators over that common denominator. There it is. So there's my algebra, and that's about as far as I can get with algebra. I've done everything I can. There's nothing to cancel. I can't cancel this with this, or I can cancel factors. It has to multiply the whole top, right? If I cancel that, it'd be like canceling the one out of here, right? All right, so that's as far as I get with algebra. Now I'll go to the trig identity. Do I say a trig identity? Yeah, awesome. If I'm clever, I can see it right here, but if I'm not clever, I can eventually get it by going to step 3. So one alternative is say, boy, that looks like something, secant squared minus tangent squared. When I see a difference or a sum of squares, often this reduces. Maybe I'll remember that tangent squared plus 1 equals secant squared. That was one of my Pythagorean identities. You need to know all the identities for this thing. Oh, I forgot to say one thing. On this test, I have skipped the section on sum to product and product to sum rules. So I didn't write that on the instructions here, but let's add this. No sum to product. We didn't cover that section. We're going to go back and do it later. I forgot to say that last time. I had it on the practice test. And I took it off because we haven't covered it yet. Or product to sum rules. There's one section on that. It's called this. I've forgotten. I hate to say the section numbers. I'm not sure. The section we skipped. All right, so here's this one. Simplify this expression. And now I remember this one. That looks kind of like the numerator there. What if I rewrote it? If I subtract tangent squared from each side, I have equivalently 1 equals secant squared minus tangent squared. Aha. This numerator is just 1. I can scratch it out and put 1 over secant squared. All right. But wait a minute, secant is reciprocal of cosine, so this is actually cosine squared. There it is. All this mess was just cosine squared. I could figure out how to graph that immediately, right? Well, with a little thinking, because it's a square. Right? So there's that one. This is for all the clever people. Well, I've done enough of this. What if I'm not so clever to recognize that looks like a Pythagorean identity? You don't have to be real clever to do all these. I'll take any proof that's correct, even if it's long, right? It takes you 2 pages, but you get it right, it's right. So how can I do that another way? If my identity fails, if I fail to recognize the identity, then I go to step 3 and rewrite it using sine and cosine only. So I'll write secant squared. So this is an alternative as 1 over cosine squared. I'll write tangent squared as sine squared over cosine squared. This is why you need to know all the identities, right? There's the quotient identity, reciprocal identity, and then secant squared is 1 over cosine squared. So I go through these steps 1, 2, 3, and now I'll go back to the top and say, I'm done with the writing in terms of sine and cosine. I go back to the top and I'll apply algebra. Oh, compound quotients. I don't want compound quotients. How can I get rid of them? And it's algebra. This class, I always tell people they really learn their algebra here because they have to, or don't make it. If you've got a common denominator cosine squared, multiply the top and bottom by cosine squared and get rid of those denominators. Cosine squared times 1 over cosine squared minus sine squared over cosine squared. Over on the bottom, cosine squared 1 over cosine squared gets rid of all the denominators, right? Because now cosine squared times 1 over cosine squared is 1. Cosine squared times minus sine squared over cosine squared is minus sine squared. And then cosine squared times 1 over cosine squared is 1. What's that? 1 minus sine squared over 1. We get rid of it. That's the other Pythagorean identity. I hear you whispering. Yeah. Cosine squared theta, right? Remember sine squared plus cosine squared equals 1? If you can't remember this Pythagorean identity, I always had trouble with that. You can remember this one. There's one of the big advantages of going to sine and cosine. You can recognize what to do easier, right? So not only does it get all in terms of two trig functions if you had like 3 or 4 of them in the equation, but you can recognize these easier. So there's the answer the long way. If you're clever, do that. If you're not, then you still get it, right? So I want you to be able to do something like that. That was 1A. I may skip 1B if that's all right, because there's another problem somewhat similar to that. You want to do 1B? Anybody wants to do that? I'm going to listen to you here. All right. All right, let's try 2. And this one I have added to what we did in class. We actually haven't covered all of this. We covered some of it, but this is a trivial problem though. It pertains to your science classes. You'll get to your science class. I don't want you to say, we didn't learn about frequency in trig. Wait a minute, what is that? I'm going to say, you did learn about it because we did this problem. Find angular frequency, and period. Yeah, you have the wave y equals 6 cosine, sine wave, pi x over 6. That slash means divide on there. It's kind of hard to see. All right, so there's the wave. The idea is that I'm only going to ask you this question if it's one of these kinds of things. Y equals a sine or cosine, bx minus c plus d. So I'll put it into that form, a, b, c, d, if I'm going to ask you this question. And then the answer to this is really easy. The angular frequency is always b. All you have to do is read. If I ask you for angular frequency, which you haven't talked about, all you do is tell me what b is. Oh, it's pi over 4. The angular frequency is b. How about the frequency? We haven't used that term before. Frequency is defined to be b over 2 pi. So we just take pi over 4 and divide it by 2 pi. And to do quotients, compound quotients like that, one way to do it is to write it as quotient of quotient, right? 2 pi is 2 pi over 1. Take top times bottom over middle times middle, right? So this is pi times 1 over 2 pi times 4. Now the pi's cancel, and we get that the frequency is 1/8. So the angular frequency you read off, and the frequency you divide that by 2 pi. And finally, the period we've already done. All right, what's the period? That 2 pi over b, we said before, right? That's how long it takes to complete one wave. Like we said, the period of cosine is 2 pi because it goes from 0 to here, 0 to 2 pi, complete one wave. So what's the period of this stretched and shifted cosine here? It's 2 pi over b, always. So we already did this one, but I just want to put it with these because it often comes with these in applications. Is 2 pi over an 8. Well, not an 8. 2 pi over pi over 4 comes out to be 8. And if you think about it, since the frequency is b over 2 pi and the period is 2 pi over b, the alternative is simply say the period is 1 over the frequency. You get 1/8 for the frequency, you get 8 for the period. I like that better. So here's what you can do for the problem is just when I ask you for angular frequency, tell me what b is, pi over 4. Calculate the period the same old way, it's 8, and then the frequency is the reciprocal of the period, 1/8. maybe that's a little faster, right? So angular frequency B, period, what you read it, period is 2 pi over B, that's just, we already learned that one. And then the frequency is 1 over the period, 1/8. All right, and the reason we do this is that this is what occurs, like if you tune your radio and it says so many hertz. What does that mean? HZ for hertz. It's cycles per second. It's how many oscillations per second the radio wave is jiggling up and down when it comes in, and it's a lot, right? It's thousands of times per second and so forth. So you see that also on your electronic box in your backyard. You look at the power boxes or your voltage coming in your house, right? So many cycles per second. All those kinds of things have frequencies. If you have an earthquake, it shakes at a certain frequency. But the frequency is 1 over the period, so I want you to have that concept. It's very easy. Read off B, compute period is 2 pi over B, and take frequency as 1 over the period. All right, there's that one. That's the only new thing today. Find the exact value of each trigonometric function. 3a. What if I would need to find the tangent of minus 75 degrees? Exactly. And by the way, if you have bought one of those good calculators and learned how to use it, you can find this exactly in your calculator. Find this exactly in terms of square roots if necessary. Here's a trick that you don't have to use, but I like to use. When I get negative angles, I never like dealing with them because they lead to lots of negatives and negatives and negatives that cancel something. I like to just pull it out from the beginning. If you have an odd function, the minus comes out. If you have an even function, you just get rid of it. So this is an odd, tangent is an odd. We'll say this is minus the tangent of 75. There's the first step. And then there's actually 2 ways to do this. So if you forget one of them, you can use the other, right? How do I know how to do tangent of 75 degrees exactly when it's not a special angle? Remember? This is another concept I want you to pull out here. I'm trying to hit all the high concepts. Right? You can do those 3.5 rules to do to be able to simplify expressions. Here's what you do if you have this kind of situation. You're going to say something?
Sum and difference?
Yeah, sum and difference formulas. Whenever this is a multiple of 15 degrees, you can do it exactly with a sum and difference formula or difference formula, one or the other. Multiple of 15 degrees. I'll write 75 degrees as 45 degrees plus 30 degrees, right? The sum of 2 special angles. And now I use the sum formula, since I use a sum here, for tangent, right? I'll put the minus out front to carry it through, but tangent of alpha plus beta, right? And what that comes out to be? Tangent plus tangent over 1 minus tangent. You have to know the identities from this chapter. You have to memorize them all, except the sum to difference and sum to product and product to sum formulas in that one section we skipped. You notice we didn't do it on the homework either. But we'll come back to that. It's actually a very fun section. It's just the least important of the whole chapter. You don't actually have to know this stuff. Well, you should know it's there. Once in a while, it's important to know it's there, and I'll show you why. Yes. Okay, so tangent alpha plus tangent beta, just put them in order, alpha, beta, over 1 minus tangent alpha, tangent beta, is tangent 45 plus tangent 30 over 1 minus tangent 45, tangent 30. And to calculate these for acute angles, you just keep in your head, you don't even have to draw the triangle if you don't want. These special triangles that we had to learn because they come up so often. There's the 30, 60, 90 triangle and the 45, 45, 90 triangle. And you can memorize these sides however you want. 1, 1 and square root 2. Or I like this one. 1 over square root 2, 1 over square root 2, 1. Or you can call these square root 2 over 2. It's the same thing. This one, 1/2 square root 3 over 2 and 1. Or you go 1 square root 3 and 2. Whichever way you like to memorize them works. And then you say, what's the tangent of 45 degrees? You can do it in your head, right? With 45 degrees, it's opposite over adjacent, it's this over itself, it's 1, right? The tangent of 45 is 1. Tangent of 30, there's the angle there, opposite over hypotenuse. Right, tangent of 30 degrees is 1/2. And now, I got that wrong, I'm sorry, it's opposite over adjacent is 1/2 over square root of 3 over 2 is 1 over square root of 3, sorry about that. So this one over this one, the angle, the side opposite 30 degrees over the adjacent to 30 degrees, 1 over this one over this one, the 2's canceling is 1 over square root of 3. All right, and now on the bottom, 1 minus tangent of 45 is 1, tangent of 30 degrees is 1 over square root of 3. There it is, an exact expression, and if you leave it like that, I'm going to take a good 2 points off, maybe 3. Why would I take points off for that when it's exactly right? It's just that it's not simplified. Often these things simplify a lot. And because they simplify a lot, I do count more than 1 point. Usually I just do 1 point for not simplifying. These things very frequently simplify. And for one thing, you do not, on any of my answers, want compound quotients, right? A quotient of a quotient like that. So first thing I'm going to do is get rid of those. How can I get rid of those compound quotients? And this is where you really learn your algebra too. You'll be good at algebra, which is the reason a lot of people fail calculus. And more than not knowing their trig, which they need for calculus, they fail even more often if they don't know their algebra. So hopefully this will work it up. I'll rewrite that minus on the outside. 1 plus 1 over square root of 3 over 1 minus 1 over square root of 3. Right? To get rid of those, the denominator, I multiply through the top and the bottom by the least common denominator, which is square root of 3. Right? If I just multiply top and bottom by square root of 3, I'll get rid of those nasty denominators. And let's see, square root of 3 times 1 is square root of 3. Square root of 3 times 1 over square root of 3 is 1. Square root of 3 times 1. Square root of 3 times 1 over square root of 3. And I've got that. That's much better. So that's a point, maybe a point more on your test, but it's still not done. How can I simplify that? If you want, you can do this. You don't have to do this. If I take minus and apply it to the denominator, I can write the denominator as 1 minus square root of 3. Let's minus the denominator. So you do that if you want. You don't have to. And then you get rid of the minus in front. It's kind of nice. Instead, what I'll do is this. Say whenever you have an a plus b square root c, what do we say? If that's in the denominator, how can you get rid of it in the denominator? You multiply the denominator by its conjugate, a minus b square root c. These are conjugate to each other. If you see this in the denominator, you multiply by this. And if you do that, it clears the denominator of all the square roots. Right? So that's what I'm going to do here. And you can also take minus these as conjugates too. And so what I'm going to do is when I see square root of 3 minus 1 on the top, I'm going to, on the bottom, I'm trying to rationalize the bottom. I'll multiply by the conjugate of the bottom, square root of 3 plus 1. This is actually minus the conjugate of the bottom, but you can do that too. So just to save a little writing, I'll multiply by minus the conjugate. But if I multiply top and bottom both by the conjugate, then I haven't changed the quotient, right? So you figure out what's the conjugate of this one. Here it is for the minus. And multiply top and bottom by that. And now what I've got, look what happens in the bottom when I multiply conjugates. Square root of 3 times square root of 3 is 3. Square root of 3 times 1 is square root 3. Square root of 3 times minus 1 is minus square root 3. And minus 1 times 1 is minus 1. The square roots cancel it. It works every time with conjugates. They cancel out all the roots. Now on the top, not so lucky, I've got square root 3 plus 1 squared. If I multiply these out, square root of 3 times square root of 3 is 3. Square root of 3 times 1. Another square root of 3 times 1. And 1 times 1 is 1. So I've got that on the top. So, there's that. 3 minus 1 on the bottom is 2. 3 plus 1, I get 4, and I've got 2 of these, so 4 plus 2 square root 3 over 2. Now you're within 1 point of full credit, right? So what do I need to do still? I can factor out, I can cancel a factor. I can't cancel this and put 2, right? You can't cancel in terms, you have to cancel factors. You need something multiplying the whole top. All right, the top is 2 plus 1 square root 3. Now, this time this is 4, this time this is square root 3. Now I can cancel, right? A factor of the top, something that multiplies the whole top. With a factor of the bottom, something that multiplies the whole bottom, I cancel those 2. And I get minus 2 minus square root 3. There's the answer. Now you see why I don't want you to leave your answer like that when the answer is expressible as minus 2 minus square root 3, right? This is actually equal to that with a lot of algebra. And a lot of these, the algebra is actually harder than the trig, right? I think that was more work, don't you? But I want you to get it to there to get full credit, okay? There's 3A. Questions is all right? So this is the hardest chapter, so I'll probably curve the test a little this time. I don't know how much, but so now I want to do one more thing. There's an alternative on this one, actually. You can, if you forget that formula or whatever, don't like it, can't get the simplification done there. Suppose I want to find the tangent of minus 75 degrees. Another way. What's the other way? Can anybody think of another way to do that? Any 15-degree angle is also half of a special angle. So I can use a half angle formula. I can rewrite this. Let's pull the minus out again just to make it easier on ourselves. So I don't wind up with a bunch of minuses later, extra minuses later. Again, you can pull it out of an odd function, right? But an even function, you can make it go away. So if it was cosine of minus 75 degrees, what would I do? I'd immediately go like cosine of plus 75 degrees. I can just drop it because cosine's even. Cosine of minus 75 is the same as cosine of plus 75, even easier. So the even functions, you get rid of your minus, and the odd functions, you pull it outside. And it saves you doing a lot of minuses later sometimes. All right, so sine of a tangent of 75 degrees, how do I evaluate that? I recognize that it's half of a special angle, right? It's a tangent of 1/2 of 150 degrees, right? Now, what's the tangent of 150 degrees? That's not an acute angle. I have to draw the unit circle. So whenever it's between 0 and 90, an acute angle, I can just draw a triangle, but if it's negative or bigger than 90, then I have to go to the unit circle. 150 looks about like that, because 30 degrees more give me 180, a straight angle. Right? So once I draw that, I drop the perpendicular, make the reference triangle. Oh, it's a 30, 60, 90 triangle because that's 30, and I drop the perpendicular to make 90. So this side must be square root 3 over 2. That side must be a half. That side must be 1. And I observe that the tangent. Oops, hold on. I have to go write this way. I use the half angle identity at this point and say the tangent of 1/2 of an angle, think of this as 1/2 theta, has this formula. It's square root of 1 minus cosine of the angle, theta, over 1 plus the cosine of the angle. Remember this half angle identity for tangent? If you forget this one, it's just a quotient of the half angle identities for sine and cosine. So I mean, sine looks like this. 1 minus cosine theta over 2 plus or minus, and cosine is plus or minus. So if you remember these two, here's the half, here's sine of half an angle, here's cosine of half angle. If you divide them, the two's canceling, you get this for tangent of half. So that's how I remember this. There are other formulas for it, but this is the easiest to remember. So I'll just say you divide the two half angles for sine and cosine. Let's figure this out. All right. Now, cosine of 150 degrees, it's this one. Oh, it's square root 3 over 2, but negative. So this is minus the square root of 1 minus negative square root of 3 over 2 over 1 plus negative square root of 3 over 2. And once again, I got lots of awful quotients in here. How do I get rid of the quotients? Multiply top and bottom by the least common denominator, this time 2, right? So I'm going to multiply the top and bottom. Now we get to do override our old messy algebra with a new messy algebra. So either way is a lot of algebra, unfortunately. So I'll write this as minus the square root and multiply the top, 1, which is 1 plus square root of 3 over 2. And the bottom, which is 1 minus square root of 3 over 2. Each by 2 to clear out the denominator. Right? So here's minus square root of 2 plus 2 times square root of 3 over 2 is square root of 3. And the bottom, 2 times 1 is 2, 2 times minus square root of 3 over 2 is minus square root of 3. There it is. What's wrong with that? Again, a plus b square root of 3 in the denominator, right? So I can't leave it like that or it's a couple points off. It's not simplified enough. And as you saw in the first method of doing this, this simplifies a lot. The answer, remember, was minus 2 minus square root of 3. Who wants to see this, right? You don't want to deliver that to your boss when the answer can be written like that, right? So, so let's see how we can simplify this. Again, how do we simplify this if there's a radical in the denominator? If it's 1 over square root of 3, you just multiply top and bottom by square root of 3 and rewrite it as square root of 3 over 3, right? That gets the radical out of the denominator. But if it's a plus b square root of 3, what do? Yeah, there you go, conjugates. So I'm going to rewrite that as 2 plus square root 3, 2 minus square root 3. And I multiply top and bottom by the conjugate of the bottom because I'm trying to clear the bottom, right? So I'll multiply by 2 plus square root 3, it's conjugate. And I have to multiply the top, cancel it, it'll change the solution, right? And now on the top, I have 2 plus square root 3 squared. And on the bottom, again, these will cancel, but 2 times 2 is 4. Plus 2 square root 3 minus 2 square root 3 is going to cancel. I don't even need to write them. Plus minus square root 3 times square root 3 is minus 3. So if I don't write out the canceling square roots, it's just 1 on the bottom. And what I have is square root of 2 plus, well, there's a minus out here. 2 plus square root 3 squared. Well, the square root of the square, they don't do each other. This is just minus 2 plus square root 3. Or minus 2 minus square root 3 is what we had before. I forgot my mind. Anyway, so sure enough, we get the same answer with a half angle and a lot of algebra also. Okay. That's why I say start early on these. A lot of these are pretty long and grungy, and the real test won't be this long. I'll give you a smattering of these. One of my friends here in the math department, it's quite funny. He's a graduate student over at OSU, and he working on his PhD, and eventually came over here and became a professor here. And he was taking one of his qualifying exams, and I had this long. You think these are bad? He's in graduate school. He gives the exam to his professor, and the professor looks at it for a minute, passes him, and he says, well, aren't you going to look at the rest of it? And he says, one does not have to drink the whole cake to know that the wine is good. So that's what we're going to do on this test. I'm just going to give you a few of these, and I'll hopefully know that the wine is good, if you understand what's going on. So I love that analogy. Maybe they'll save us some work here on the test. I don't have to test you in all of these. All right, so there's that one. Let's you want to do the one in radians, cosine 7 pi over 8? Maybe we should do that one. 3b. Evaluate exactly. Again, you're bring your fancy calculator if you have one, the one with the computer algebra system, and check all these answers. It will tell this to you exactly if you leave it in the exact mode or the best mode where it gives exact if it can. It has 3 modes. It can give you the exact answer always and give up otherwise. It can give you the exact answer or the decimal if it can't figure an exact answer, like it's not a special angle. But for these half angles, it will do them exactly. It will do all your algebra for you and everything. And you can check all these, or you can put it in approximation mode, then it only gives decimals. All right, So 7 pi over 8, how do I know that I can do this one exactly? This is actually not a multiple of 15 degrees. I don't try the sum or difference angles on this one, of angles on this one. Right? How do I know I can still do it exactly? Because it's still half of an angle. So I remember that if it's a multiple of 15 degrees, which is pi over 12, right? 30 degrees is pi over 6, so 15 is pi over 12. If it's one of those, I can use either the sum or difference formulas or the half angle identity. But the other thing you can do, this one actually is 1/2 of 7 pi over 4, 1/2 of a special angle that's not a multiple of 15 degrees. With a multiple of 15 degrees, this would be a multiple of pi over 12, but it's not, it's a multiple of pi over 8. So I recognize this one is still half of the special angle 7 pi over 4, and I still use a half angle identity, but not the sum or difference identity. That's what you do on these. If it's a multiple of pi over 12, then it's multiple of 15 degrees. But this is a half of something else. It's a half of 315 degrees. Right? Anyway, so how do I do that when I have a half angle formula for cosine, right? It's square root plus or minus 1 minus cosine of the whole angle, 7 pi over 4, all over 2. That's the half angle identity. Cosine of 1/2 theta is 1 minus cosine theta over 2 square root plus or minus. Hopefully that looks familiar. All right, so now I have to do an angle that's not an acute angle. I have to run to the unit circle here, and I'll say 7 pi over 4. Where is that? You can break this up into pi plus pi over 2 plus pi over 4. That's a mess. It's easier to say 8 pi over 4 would be 2 pi, a whole rotation. So this is pi over 4 short of 8 pi, right? If I put 7 pi over 4 there, pi over 4 here completes 2 pi. So that's where that's at. And now to compute the cosine of 7 pi over 4, I drop the perpendicular, make my special triangle, and say for this one, it's 45-degree angle. It's square root 2 over 2, or 1 over square root 2. Square root 2 over 2 and 1. And the cosine must be this square root 2 over 2, or 1 over square root 2, whichever way you like to write it. And I'll say, you see this is getting kind of, okay. Worry about that red and the glare here. All right, so this is plus or minus square root 1 minus, and the cosine is plus here, right? Because it's in the fourth quadrant. 1 over square root 2. All over 2. There we go. And then there's a plus or minus in front. Be careful on this one because people often they say, oh, look, cosine was positive. We'll put positive, but it's actually negative. Why? Because the sign we're picking here is we're trying to make it match on the original angle. The cosine is 7 pi over 8. The original angle is in the second quadrant, right? 8 pi over 8 is a straight angle. This is almost a straight angle. Since we're in the second quadrant, cosine has to be negative, right? Drop the perpendicular there, then it's negative. So don't go by the whole angle, go by the half angle that we're trying to evaluate the cosine of. And we put negative out here, right? Quadrant 2. Now, how do I deal with that? Again, I can multiply top and bottom by square root 2 to get rid of the quotient, but there's a trick on this one. It's easier to multiply top and bottom by 2. Let's rewrite this as minus square root of 1 minus 1 over square root 2 over 2. Multiply top and bottom by the same thing too, and that will also clear out the denominator, but it'll make this denominator easier is why I did that. It'll make this a square down here. So minus square root of 4 on the bottom, and 2 times 1 is 2. 2 times 1 over square root 2 is square root 2. I should point that out, right? 2 times 1 over square root 2. Square root 2 times 1 over square root 2. Those cancel and you get square root 2. So that's what I did here. Now, I don't need to try and rationalize a numerator, you only rationalize denominator, right? So I'll leave that the way it is. Except square root of 4 is 2, so I can rewrite this as I have the square root of the quotient is the quotient of the square roots for positive numbers. So this is minus square root of 2 minus square root of 2 all over 2. There it is. 2. How about that? Now, technically, a lot of the problems that wind up with this square root of a square root simplify. Not always, but it's very difficult algebra. And I don't want to spend our time on too much algebra, so I'm going to take the answer just like that. Even though some of these square roots with square roots do simplify with a lot of work, it's not worth learning the algebra technique. So I left the answer, I think, in the answer key just like this. And I don't remember if this one simplifies or not. Some of them don't. That's the trouble. Sometimes they do, sometimes they don't. It's a lot of work to find out. Don't do it. All right. So there's that one, right? I want to do number 5 here. This is an easy one, but it's I want to make sure you get the easy ones. You hate to lose a bunch of points over something else. This is exactly the kind of thing that comes up in your classes later too, that we always see this thing in calculus when it says cosine 5x, cosine 3x, minus sine 5x, sine 3x. And the instructions are to write as a single trig function, or in a sense, it's simplified. How about that? This is the reason that for your future classes, you want to memorize all those identities and practice them. If you do, then you might recognize immediately. This looks like something I've seen before, right? What have I seen? Where have I seen that before? Cosine minus sine, right? I know I've seen that in identity somewhere. If you got those memorized, think of this as cosine minus sine is the sum identity for cosine, right? On the sum identity, on the cosines, this plus goes with minus and minus goes with plus. So this is actually cosine of 5x plus 3x. So you just memorize that cosine alpha, cosine beta, plus sine alpha, minus sine alpha, sine beta was cosine of, oh, wait a minute, this is plus on here. Wait, I just read that. Let's see. No, that's all right. Let's see. Yeah, this was plus. Those straight bars, I can't see them from the straight angle. This was plus, and so this one's minus. Let me follow the problem that's on there. So cosine plus sine is the difference identity for cosine. So this is cosine of 5x minus 3x or cosine of 2x. Much easier, right? I know how to graph this immediately. All I do is take the cosine function and the x replaced by 2x makes half the period. So it's just cosine function with half the period. It just goes like that. And so, oops, that's the sign. There we go. It just goes like that over and over, and it repeats every pi units instead of every 2 pi units. That's a whole lot easier to graph than this, right? So that's one of the reasons you want to be able to simplify these. All these things combined, and this is one of the amazing things about trigonometry, multiply and add these things. Sometimes it comes out real simple like that, just a single wave. And electronics engineers that do these, these oscillating circuit things, they can get this all the time and have to simplify it and see what oh yeah, it's just a, alternating current or something. Right? Okay, so there's that one. Isn't that easy? Just recognize the identity. If you've done those enough, is cosine plus sine. I've seen that. Guess we can do 6. I'm almost tempted not to. But you want to know all those different identities. We did sum and difference identities, then we did half angle identities and double angle identities. We skipped the sum to product to sum identities. Then we used all these things to solve trig equations. That's the chapter. Here's square root of 1 plus cosine 5 pi over 12 all over 2. And suppose the instructions here are simplify with a half angle identity. You get hit on this one. Don't like that one. I just want to rewrite it in a better form. What can I do? It's the what does it look like rule, right? What does that look like? I know I've seen that before. Instead of cosine, cosine plus sine, sine, this is another identity that looks like this. What I recall is that cosine of 1/2 theta is plus or minus the square root of 1 plus cosine whole theta all over 2, right? That's the half angle identity for cosine. So it looks like, just like that, where theta is 5 pi over 12. Right? So it follows that this must be equal to cosine of 1/2 theta. Right? Except, alas, the plus or minus. What do I do with that? Here's what you can do, and this is a little tricky. That's why I put it on here. The plus or minus can go on either side, right? If this is equal to plus or minus this, then this is equal to plus or minus this. So I put plus or minus over here. And now I say, well, should this be a plus or minus? What one is it? You figure that out by the quadrant. Let's rewrite this. This is plus or minus cosine of multiply top times top over bottom times bottom, and you get 5 pi over 24. And this one, remember this radical, what does it mean? What does that radical sign mean? It means the number whose square is this, the non-negative number, right? If you want, like, if you write square root 4, that gives you 2. If you want the other number whose square is 4, you write minus square root 4, right? So this number is always non-negative. And so this is going to be, since this isn't going to give us 0, this will be a positive number, right? So this is positive. I want my result to be positive. So if this is negative, I'll choose negative to make a positive to match this. If this is positive, I'll choose positive to match this. Is cosine 5 pi over 24 positive or negative? Well, this is less, right? It's in the first quadrant. 12 pi over 24 would be a 90-degree angle. So this is certainly less than 90 degrees. This is in quadrant 1. So it's going to be positive. All trig functions are positive in quadrant 1. I need to choose the plus sign to go with it. So the answer is this is exactly equal to cosine of 5 pi over 24. That's a way to simplify this. Who wants to write this in your engineering class when you can write it like that, right? That's better. Anything's come up on the homework you want to look at it? I'm trying to stress a lot of concepts that you can take a trig function of half of any special angle. You can take a trig function of any mobile of 15 degree. You can simplify these trig expressions using the 1, 2, 3 rules or 3.5 rules with 0. You can recognize a trig identity and just simplify immediately. Here's another thing you can do. Put it up on the screen over there. This is number 7. If you're given a trig function and a quadrant, you can find any other trig function or a trig function of half or double an angle. So here's what we have is if secant x is square root 5 over 2 and sine of x is negative. So that'll tell me the quadrant between these two. Find exactly the sine of 2x. I like this problem because you can't just do it on your calculator like the last one, right? You have to know everything yourself. And this is why you can't just memorize formula and have a calculator do everything for you. You have problems like this where the calculator can't do it, right? So you have to know the trig identities for this. Here's what somebody's going to do on the test. I'm going to try and hit off as much of this as I can. Oh, this is 2 sine x. I just have to calculate sine x, right? What's wrong with that? It's not true, right? Double angle identity. What's the sine of 2x? It's 2 sine x cosine x. This is a good illustration. You can't just pull a number out of here. It's not like that, right? It's like square root of 2x. Oh, it must be 2 square root x, right? No, you can't pull things out of the square root. This is a function too. You can't pull the 2 out. use the double angle identity. It says sine 2x is 2 sine x cosine x. That's the identity we proved. You prove this using the sum of angles formula. Just put x equals y and sine of x plus y equals sine cosine plus cosine sine, and you get this one. So this is the thing we proved in class from the sum of angles formula. Now I've got all I need is sine x and cosine x. So how am I going to find those? I think you know it. Well, I'm given secant. Once I'm given one trig function and quadrant, I can find all 6 of them, right? Remember that? For instance, I could find cosine x by taking this reciprocal. Cosine is this upside down, 2 over square root 5. Once I know cosine, I immediately know sine by the Pythagorean identity, solve for sine. Remember, sine x is plus or minus square root 1 minus cosine squared. So I can figure it from the cosine. So that's what you do. You give one of these, you find sine and cosine, then you get all the rest. Well, let's see. This is plus or minus square root 1 minus 2 over square root 5 squared. And I just calculate away. Well, is it plus or minus? I was told, right? If I have a quadrant or if I'm just told the sign directly, I know, oh, it's negative, so I have to throw that out. This is given that it has to, sign has to be negative. So we'll put a minus out here. That's just to get another point out of you. Let's make sure you know everything. All right, so I just have to simplify this now. How can I simplify that? Fortunately, the square takes care of the square root in this case. I don't need to do conjugates again, right? 1 minus square root of 2 over square root of 5 is 1 minus 4/5. This is minus the square root of 1/5, right? And you want to simplify this, right? When you have a square like 1, you want to write it as square root of 1 is 1 and square root of 5 is leave it like that. So it's minus 1 over square root of 5. There is the sine. There's the cosine. You put those in and say it's twice sine minus 1 over square root of 5. Two times sine times cosine is, let's see, right? And to multiply these, think of this as 2 over 1. It's top times top times top over bottom times bottom times bottom is minus 4 over square root of 5 times square root of 5 is 5. The answer is exactly minus 4/5, right? How about that? It actually came out to be a nice fraction. But that's how you can do that one. Given it, you just want to get the concept down. Given a trig function in a quadrant, I can find all 6 trig functions like this. And I can find trig functions of double angles then and half angles using the double and half angle formulas. It's like that Master Chef program, right? You have to have all the recipes down and oh, if I see this, this is what I'm going to do to bake a pie. If I see that, that's what I'm going to do to cook a fish, right? You see that, you know how to deal with it. Just these basic concepts. Here's one I want to stress, though. This is kind of tricky, and I think some people kind of gloss over it and say, I can do this one. I said you can do that, but be sure you're right, because this one's tricky. Let's use this again. Indeed, you know, on these ACT and other tests where they test your skills, they always try and fool you on these things, you know. So this is a kind of fooler question they have. What about what's the inverse secant of 3? This is not a number that comes from a special angle. So I'm going to say let's approximate it to 2 decimal places. I think I said approximate. I want to be able to do approximations. This is not 2 significant digits, right? This is 2 decimal places. There's a difference, which we'll point out in a second. How can I do the inverse secant of 3? A lot of you did these things on the homework and said, oh, just put it on the calculator. There's no inverse secant in your calculator normally. What do I do? I'll let theta say. Well, if inverse secant of 3 is equal to theta, it follows that 3 must be the secant of theta, right? which by reciprocals now says that 1/3 is equal to cosine theta. Reciprocal to the left equals reciprocal to the right. Now I've got it because that means that theta is the inverse cosine of 1/3 that is in my calculator. How about that? So I'll convert it from an inverse secant to an inverse cosine that's on there. Now my calculator, I put second cosine, because above the cosine in the same color as this key is the inverse cosine. So I push this one followed by this one, it invokes the inverse cosine. 1 divided by 3. On some calculators, you need to close the parentheses, depends on how old it is usually. Enter. There it is. And let's see what we get out of that. I got theta, or inverse secant, of 3, not from a special angle, is 1.23095, etc. Lots of digits. 2 decimal places. If I said round to 2 significant digits, you start from the first non-zero digit on the left and count 1, 2, and round to here 1.2. That's 2 significant digits. 2 decimal places means 2 digits right at the decimal point, so I round it here. And if this is 5 or greater, I round up to 1.24, but it's not, so I'll say this rounds or is approximately equal to 1.2. That's the answer I want to see. I want to round it correctly to the number of places I tell you, because that's what they'll do with business. So I rounded to so many decimal places. 1.23. Easy as 1, 2, 3. Okay. There's a formula for this also, but I think it's easier to memorize the trick. So I'll say just rewrite it as inverse cosine, right? When it's not on your calculator, and when inverse secant isn't on your calculator. Now the first one, when it has inverse tangent of 0.8, you just use the inverse tangent button directly. That's an easy one. So, all right, find an exact expression in degrees. Let's see. I'm gonna make sure I have enough time for the nasty ones at the end here. I'm gonna skip that one. I'm gonna go ahead to some of these other ones. I want to make sure we cover. Here's 11B. These are the hardest problems of the whole thing. Save them to the bitter end here. This way, you won't have to be depressed the whole period if I put them at the end. So here's
Just the rest of the day.
here's 11B. Suppose I'm solve exactly. Here's another one. You can't do it on your calculator. You have to do a lot of work on this one. Secant 2 theta is minus square root 2. Theta restricted between 0 and 2 pi, so it's in radians, the harder case. Right? But radians is exactly what you need in higher mathematics. Higher mathematics, we almost always use radians. For a reason you'll find out in calculus. The formulas are all easier in calculus if you do it right. All right, so how do I solve that exactly? Remember, we did all those different steps. If it's trig function equal a number, you solve it on the unit circle, but not right, that was method 1. But first you want to get a single angle. So we'll get a single angle, I'll let u equal 2 theta and rewrite. This is why you need to practice these, is have a bump of direction. If baking a pie, I gotta put this in first, right? Secant u equals minus square root 2. Get a single angle as the first step, not a double angle. Now I can try and solve it on a unit circle, right? But last drawing secant on the unit circle, what we usually do for secant and cosecant is write their reciprocal, right? So these are equivalent, meaning it has the same solution set. I'll rewrite this by saying the reciprocal of the left cosine u is the reciprocal of the right minus 1 over square root 2, which I now recognize comes from a special angle, so I know I can do this exactly, right? What do I do for that? I solve it on the unit circle, we said. Once you have trig function equal a number with a single angle, solve it on the unit circle. Here it is. Cosine u is minus 1 over square root 2. Cosine is the x coordinate in the unit circle. That's why I put it in terms of cosine so I can do this. And x equals a number is a vertical line in the plane, right? And 1 over square root 2 is about 0.7. So this is about minus 0.7 here when I draw the line. X equals minus 1 over square root 2. These are all points in the plane whose x coordinate is minus 1 over square root 2. You try and draw these approximately, you don't want to, it doesn't have to be real accurate, but you don't want to draw it on this side, you'll fool yourself, right? So draw on the right side about as far over as you think it is, about minus 0.7 here. And now you observe there's exactly 2 points in the unit circle that have that x coordinate, right? So there's exactly 2 terminal rays, this one, and that's it. Those are all the terminal rays that can make secant u equal minus square root 2, and consequently cosine u equal minus 1 over square root 2. I want to find those angles u. Here's an angle u equals something, and here's another one. There's 2 within 1 rotation. If I want this angle here, I can figure, since x equals minus 1 over square root 2, that means this side length is plus 1 over square root 2, right? Or they go over to minus square root 2 from 0. That being the case, and this is a unit circle 1, I recognize this can only be a 45, 45, 90 triangle. The Pythagorean theorem forces this side to also be 1 over square root 2. And this is a pi over 4 angle. On these things, don't waste your time doing a second triangle. There's always symmetry. This is the other reason you draw it carefully. You don't want to think, oh, maybe this is the symmetric angle. You draw it nicely, then obviously this is the symmetric angle. This is also pi over 4. Knowing that, I can see exactly what u is, right? Pi back up pi over 4. Well, 1 pi less a quarter pi is 3/4 pi. Or it could be pi plus pi over 4. 1 pi plus a quarter pi is 5/4 pi. So there's exactly 2 values of u within 1 rotation. That's right. You can get to this terminal ray or this terminal ray, and that's it, right? Within 1 rotation. But when you have to substitute to get a single angle, this is the hard case. That's why I picked this one. Some of these other problems are easier, so don't let me scare you too much. Doing the hard ones mostly. When you have to substitute there, you have to go back now and find all angles u. What are all possible u? Because any coterminal angles will also give you the same trig functions, right? All coterminal angles give the same values for all the trig functions. So all angles u are the ones I found: 3/4 pi and 5/4 pi. So you say you can be that or that. Plus, if any whole rotations, k times 2 pi rotate 2 pi radians per rotation. There's, or k is any integer again, 0 plus or minus 1 plus or minus 2. Those are all angles u that will make the secant of u equal minus square root 2. But wait a minute, we were solving for theta, right? So now I've got to go back and say, well, this is 2 theta. And now I can solve for theta by dividing by 2, right? You divide the whole side of the equation. And you say the left side becomes theta. This divided by 2 is 3 pi over 8. 2k pi divided by 2 is k pi. So you divide the whole side by 2. Or I can have the second one. 5 pi over 4 divided by 2 is 5 pi over 8. 2k pi over 2 is k pi. There's all angles theta. But wait, I restricted theta to be between 0 and 2 pi. This problem is actually easier if I say find all angles theta, because I've got them here. Now I restrict to 2 pi at the bitter end. All theta between 0 and 2 pi radians. You can leave off the units when it's radians. If it's degrees, you put degrees. What are all angles theta? Or put it up there. What you do is you try the various values of k beginning around 0. I'll try k equals 0. I get 3 pi over 8 plus 0 pi is 3 pi over 8. That's between 0 and 2 pi. Then I'll try k equals -1. Well, negative pi plus 3 pi over 8 is a negative angle. That's not allowed. It's supposed to be, I think, greater than or equal to 0. So I'll try, so I can't go negative. I start 0 work. I put k equals 1. I've got pi plus 3 pi over 8. Well, pi is 8 pi over 8 plus 3 pi over 8 is 11 pi over 8. That's between 0 and 2 pi, right? 2 pi would be 16 pi over 8. I'll try k equals 2, but 2 pi plus a positive angle is too big. So that's it. Here's the values of k down here if you want, just for comparison, 0 and 1 in the first. So I can't go negative, I can't go bigger than 1. That's it. That's all the values of k that'll make this between 0 and 2 pi. Same thing here. I put in k equals 0. I get 5 pi over 8. That's between 0 and 2 pi. That is this one. If I put k equals -1, this will give me a negative angle. That's too small. I have minus pi plus fraction of pi. If I put k equals 1, I've got 8 pi over 8 plus 5 pi over 8 gives me 13 pi over 8. And that's okay because that's less than 2 pi, 16 pi over 8. But if I put k equals 2, 2 pi plus something is too big, right? It's bigger than 2 pi. So that's it. There's exactly 4 solutions to that. You might say, why didn't we just solve for theta between 0 and 2 pi in the first place? Why do we have to find all of them, throw it out? The reason is this substitution. If you have to make this substitution, then you have to do that. If there's no substitution, you just take these angles. But what happens is if I solve here for u between 0 and 2 pi, I won't get all the answers. I'll only get 2 of those. Because as u goes between 0 and 2 pi, theta goes between, it is 2u, it goes between, or u is 2 theta. Theta only goes between 0 and pi, as u goes between 0 and 2 pi. Let's see, I got that backwards. Yeah, it'll only give me a theta between 0 and pi, and I'll miss 2 of those answers. So this is, what's easiest is just find all the answers and throw the extras out, but you could let u go between 0 and 4 pi if you wanted, and then you get theta between 0 and 2 pi. I think that's harder. And I think we've got time for one last problem here. And this was k equals 0 and 1 in the second equation. The last kind I want to do is one like this. Anybody try any of these and have a particular one? Some of these are pretty hard. Even this last one, you think that looks easy, but 14a here. Suppose I take 2 sine squared theta minus sine theta minus 1 equals 0, and I said solve this for theta between 0 and 2 pi. This is a little trickier problem because it's got a sine squared in it, right? Before it was just trig function equal to number. We know how to solve that. We get a single angle and run to the unit circle, right? But this one, it's got sine squared and sine. What do I do?
Reduction?
Hmm?
Reduction formula?
I was gonna say make a substitution. What you recognize when you see the squares, if you let u equal sine theta, this becomes a quadratic equation. So recognize when there's a square and a regular function, you can rewrite it as a quadratic equation. 2u squared minus u minus 1 equals 0. All right. Quadratic equation. I can solve that by the quadratic formula or maybe by factoring. All right. The quadratic formula always works. You need to know it for the exam. U equals, if you call this A, B is minus 1, C is minus 1. Quadratic formula says U is minus B plus or minus square root. I told you to learn algebra here. B squared minus 4AC all over 2A. This is such an important formula in mathematics. It comes up so often, such as here. Comes up a lot in calculus. They expect you to know it. So let's see what it is for this one. A is 2, B is minus 1, C is minus 1. So it's minus B is plus 1. Plus or minus square root B squared is minus 1 squared. Minus 4 times A. 4 times A times C. All over 2A. And we get 1 plus or minus square root 9 all over 4. Square root 9 is 3. So at the plus, I get 1 plus 3 over 4 is 4 over 4 is 1. 1 minus 3 gives me minus 2 over 4 is minus a half. So there's two solutions. I want to see it by factoring. The alternatives use factoring. You can factor it as blank u plus blank, blank u plus blank equals 0. That or factored. Either one works in this case. Sometimes it's too hard to factor. But in here, in these blanks, remember the product is equal to lead coefficient 2. So I'll put 2 in one and 1 in the other. And the product of the last ones has to be minus 1. So 1's going to go in one and minus 1 in the other, unless it's one of these ones with a nasty square root that you can't figure out how to factor. But here the product of these has to be the constant term minus 1. So I can put minus 1 here and 1 here, or I can put minus 1 here and 1 here. And I pick the one that gives me the minus u in the middle. Let's see, if I put it like this, it's 2u squared plus 2u minus u is plus u. That's wrong. Must be this one, right? So I FOIL it to check. 2u squared minus 2u plus u is minus u. And then minus 1. That times that. First, outside, inside, last. All the possible pairs. So there's how it factors. We'll write it. We can write it. And then by the zero product property, here's it written out a little cleaner. Either u is minus a half to make this product, this factor 0, or u equals 1 to make this factor 0. Sure enough, it's the same thing I got by the quadratic. So now, once I know the values of u by either method, this tells me u was sine theta. So this tells me equivalently now that sine theta equals 1 or sine theta equals minus a half. That nasty quadratic equation was equivalent to a trig function equals a number, or trig function equals a number. So that's what we've done with the quadratic formula or factoring. Is rewritten as trig function equal a number, go back to method 1, right? Which is you solve it on the unit circle. This time we don't have to, we have a single angle, so we don't have to find all angles and throw out the x's. We just solve it and we're done, right? So how can I get y equals 1? Sine is the y coordinate. I draw all points y equals 1. Oh, look, there's only one point on the unit circle this time because it just is tangent to it. So what angle is that? That makes sine theta equal 1. Yeah, 90 degrees, or I'll put it in radians, pi over 2. So one solution is theta equals pi over 2. Now here I got sine theta, the y coordinate can be minus a half. That'll also give us solutions, right? So I'll draw the line of all y coordinates minus a half, halfway down here to minus 1. And say, well, this time there's 2 points in the unit circle that have that terminal, that have that y value. Hence, 2 possible terminal rays, this one and this one. What are those angles? Drop your perpendicular, make a reference triangle and say, oh, if this goes down a half unit, this side must be a half. This is 1 because it's a unit circle. Pi over 6, right? It's 30-degree angle. So you can say the angle is minus pi over 6 since it's clockwise, but that's not between 0 and 2 pi, which the problem asks. So instead, I'll take this angle, 2 pi, back up pi over 6. It's 11 pi over 6. I'm running out of time, so I'll just write that out quickly. And then by symmetry, this one must also be pi over 6, right? These are the same. So I've got pi plus pi over 6 for the angle of this one. Oops. Quickly again, it's 7 pi over 6. So there's 2 solutions on this one. 5 pi over 6. Oops. 7 pi over 6. And 11 pi over 6. 3 answers, pi over 2, 7 pi over 6, or 11 pi over 6. How about that? These quadratic equations are tricky, but the idea is you write a quadratic equation by substituting u. by the quadratic formula factoring, it leads to trig function equal to number, or trig function equal to number. You just solve it on the unit circle by the previous. There it is. Go try those out and bring questions to me, right? I have an office hour immediately at the end of the hall if you have questions on any of this. But, see you soon. I put this online if you want to get it.